Computer number system and its types. Number systems are the technique to represent numbers in the computer system architecture. Every value that you're saving or getting into for memory has a defined number system. Computer architecture supports following number systems. These are binary, octal, decimal, and hexadecimal number system. Let's move on to binary number system. A binary number system has only two digits that are 0 and 1. Every number represents with 0 and 1 in this number system. The base of the binary number system is 2 because it has only two digits. Octal number system. Octal number system has only 8 digits from 0 to 7. Every number represents with 0, 1, 2, 3, 4, 5, 6, and 7 in this number system. The base of the octal number system is 8 because it has only 8 digits. Decimal number system. Decimal number system has only 10 digits from 0 to 9. Every number represents with 0, 1, 2, 3, 4, 5, 6, 7, 8, and 9 in this number system. The base of the decimal number system is 10 because it has only 10 digits. Hexadecimal number system. A hexadecimal number system has 16 alphanumeric values from 0 to 9 and A to F. Every number represents with 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, and A, B, C, D, E, and F in this number system. The base of the hexadecimal number system is 16 because it has 16 alphanumeric values. Here A is 10, B is 11, C is 12, D is 13, E is 14, and F is 15.
Decimal number system. It is uses 10 digits from 0 to 9. It is written with a subscript of 10 since it's composed of 10 digits. This is an example of decimal notation. 12 sub 10, 350 sub 10, 30.2 sub 10. Decimal equivalent is sum of product of these digits with decreasing power of 10. We have given here 7203 sub 10. So we have the following digits 7203. So we will multiply these digits to decreasing power of 10 and this will be the outcome. 7 times 10 raised to 3, 2 times 10 raised to 2, 0 times 10 raised to 1, 3 times 10 raised to 0. After that, this will be our value, 7,200, 0, and 3. Then the sum is 7203. As you can see, this is equal to the given digits in the first place. We just proven that the decimal number is typically uses base 10. Binary number system. It is consists of two digits, 0 and 1. It is written with a subscript of 2. This is an example of decimal notation. 101 sub 2, 11011 sub 2, 101010 sub 2. Let's just say this given value 11010. Each one of them is what we call bits. On the rightmost value is the least significant, while on the left side is considered the most significant. We have here the table reference that gives us the given value from decimal to binary. So it's just a reference. Decimal equivalent is sum of product of each digit with decreasing power of 2. We have given here 11011 sub 2. So we have the following digits 11011. So we will multiply these digits to decreasing power of 2 and this will be the outcome. 1 times 2 raised to 0, 1 times 2 raised to 1, 0 times 2 raised to 2, 1 times 2 raised to 3, 1 times 2 raised to 4. After this will be our value. 1, 2, 0, 8, 16. Then the sum is 27 sub 2. So the 27 is equivalent decimal value of this given binary number. Octal number system. It is consists of 8 digits 0, 1, 2, 3, 4, 5, 6, 7. It is written with a subscript of 8. This is an example of octal notation. 751 sub 8, 256 sub 8, 32 sub 8. We have here the table reference that gives us the given value from octal to binary. Decimal, it is just a reference. Decimal equivalent is sum of products of each digits with decreasing power of 8. We have given here 526 sub 8. So we have the following digits 5, 2, and 6. So we will multiply these digits to decreasing power of 8. This will be the outcome. 6 times 8 raised to 0, 2 times 8 raised to 1, 5 times 8 raised to 2. After that, this will be our value, 6, 16, 3 to 0. Then the sum is 342, sub 10, in decimal number. So, 342 is the equivalent decimal value to this given octal number. Hexadecimal number system. This consists of 16 digits, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, A, B, C, D, E, F. It is written with a subscript of 16. This is an example of hexadecimal notation. 20FB sub 16, AC2 sub 16, 2E4D sub 16. We have here a table reference that gives us the given value of hexadecimal to binary. So this is we can use this on the conversion that Jara and Fred will tackle about. So decimal equivalent is sum of product of each digit which decreasing power of 16. We have given here F4 sub 16. So we have the following digits which is F and 4. So we will multiply these digits decreasing power of 16 and this will be the outcome. 4 times 16 raised to 0, 15 times 16 raised to 1. After that, this will be our value 4 and 240, 240. Then the sum is 244 sub 10 in decimal number. So 244 is the equivalent decimal value to this given octal number.
The number system conversion. The conversion of binary number to decimal number. As we all know, the binary system number is 2 because it has only 2 digits. So we need to know the power of 2 table to easily convert the binary numbers. So the power of 2 table are 2 to the power of 0, 2 to the power of 1, 2 to the power of 2, and so on. So let's start. Given the example of binary number 1010, first you need to put the appropriate values of each numbers. Now, inputting the values, start at the least significant bit or the number on the right side, going to the most significant number or the number on the left side of the given binary number. Multiply the binary numbers by its values. 1 times 2 to the power of 3 is equals to 8, and 1 times 2 to the power of 1 is equals to 2. As you notice, the zeros are not included because in putting the equivalent, we can disregard the zeros because it is off and doesn't have value. So let's focus on the number that has 1. To get equivalent into decimal, add the two numbers, which is 8 plus 2 is equals to 10. So that's it. If the binary number is 1010, the decimal number is 10. Now let's proceed to the conversion of octal number to decimal number. If the binary has base 2 system, octal number has base 8 system. Let's have an example. Given the octal number 370 sub 8, so the values would be 0 is equals to 8 to the power of 0, 7 is equals to 8 to the power of 1, 3 is equals to 8 to the power of 2. Now multiply the given octal number by its values. So 0 times 8 to the power of 0 is equals to 0. 7 times 8 to the power of 1 is equals to 56. Then 3 times 8 to the power of 2 is equals to 192. So add 0 plus 56 plus 192 is equals to 248 sub 10. It is sub 10 because the decimal number system is 10. So that's it. If the given octal number is 370 sub 8, the decimal number is 248 sub 10. Lastly is the conversion of hexadecimal number to decimal number. Before we convert the hexadecimal number to decimal number, we need to know their relationship first. 0 is equals to 0, 1 is equals to 1, 2 is equals to 2, and so on until 9. Then 10 is equals to A, 11 is equals to B, 12 is equals to C, 13 is equals to D, 14 is equals to E, and 15 is equals to F. Now given the example of hexadecimal number 2, 3, E sub 16, the subscript is 16 because hexadecimal has 16 alphanumeric values. So now the values are E is equals to 16 to the power of 0, 3 is equals to 16 to the power of 1, 2 is equals to 16 to the power of 2. Now multiply it. 2 times 16 to the power of 2 is equals to 512. Then 3 times 16 to the power of 1 is equals to 48. Then the value of E, as we know their relationship, E is equals to 14. Now 14 times 16 to the power of 0 is equals to 14. Note that any number that raised to the power of 0 is equals to 1. So now add the equivalents. 512 plus 48 plus 14 is equals to 574 sub 10. So if the given hexadecimal number is 23E sub 16, the decimal number is 574 sub 10.
Hi guys, I am Fred Anthony Liu, the last reporter of this video presentation. So, the last three reporter discussed about what is number system, each type of number system, and the conversion of binary, octal, hexadecimal number system to decimal number system. So, now, I am going to teach you how to convert decimal number system to binary, octal, hexadecimal number system. So first, we will convert decimal number system to binary number system using the successive division method. So let's say we have the number of 348 with a base of 10, or with a subscript of 10, I mean. So it is subscript of 10 because it represents the decimal number system. So now let's divide this one. 348 divided by 2. So for your information guys, I get this 2 from the binary number system because it represents the base of 2. So we can call it. So we will have the quotient of 174 with no remainder. And let's continue to divide it. So these two numbers, the quotient is 87. With still no remainder. 87 divided by 2. So now we will have a remainder. So it is 43.5 actually. So but it is the remainder. So how did I get the remainder of 1? So I multiply this 2 to the after the decimal point. So 0.5, 2 times 0.5 is equals to 1. So now let's continue to divide this 2, and we will have the quotient of 21 with a remainder of 1. 21 divided by 2, we will have the answer of 10 with a remainder of 1. And 10 divided by 2, we will have the quotient of 5 with no remainder. And 5 divided by 2 is equals to 2 with a remainder of 1. And 2 divided by 2 is equals to 1. A quotient of 1 with no remainder. And 1 lastly divided by 2 is equals to 0. 0.5 with the remainder of 1. So this the last the last remainder is the most significant bit. We will read this from bottom to top. So, and this is the first remainder or the first answer is the least significant bit. So let's read this from bottom to top. So 101 101 0111 0111 and 00. So this is the conversion this is the conversion of decimal number system to binary number system. So this is now the binary number system, guys. Yeah. So wait, I will just highlight this answer. So you can see it fully. So just as simple as that, you can convert the decimal number system to binary number system. So now, after the last conversion, let's convert now the decimal number system to octal number system. So let's say we have the number of 348 with a subscript of 10. So we will still use the successive division method to convert this. So 348 divided by 8. So I get this number of 8 from octal number system because it is base of 8. So now, so we will have the number of 43.5. So it is equal of 43 with a remainder of 4. So like what I said earlier, I get the remainder from multiplying 8 to the number of the number after the decimal point. So 8 multiplied by 5 is equals to 4. So now let's continue. 43 divided by 8. So it is equals to 375. So now it is equals to 5 with a remainder of 3. So let's continue. 5 divided by 8. It is equals to 0.625. So it is 0 with a remainder of 5. So yun na. So like what I've said earlier, we will read this from bottom to top. So this is the most significant bit, and the upper part or the first result from earlier, the first answer earlier is the least significant bit. So now after we get the answer, we'll read this as read this as 5, 3, 4 with a base of 8 because it is now octal number system. So from 348 with a base of 10 because it's decimal number system. Now is 534 with a base of 8. So let's proceed to the other conversion or the last part. So now the last part of the conversion, let's convert decimal number system to hexadecimal number system. So let's say we have still a number of 348 with a subscript of 10. So let's still use the successive division method to convert this. 348 divided by so 16 now because it is the base hexadecimal number system basically is base of 16. So now the quotient of these two numbers is 21.75. So basically it is 21 with the remainder of 12. So then let's continue to divide and to get the answer. 21 divided by 16 is 1.3125. It is 1 with a remainder of 5. So now the last part is 1 divided by 16. So it is basically with no answer, with no decimal point, is equals to 0 with a remainder of 1. And let's read this upwards like what I've said earlier. This is the most significant bit and this is the least significant bit. So let's read this. 1, 5, 12. So because 12 is more than 9, we can't use this number because it is more than 9. So like they discussed earlier, 10 is equals to A, 11 is equals to B, and 12 is equals to C. So we'll get this one. So now it is 1, 5, C with the base of 16, subscript of 16. So in the decimal number system, it is 348 with the subscript of 10. And now it converts to 15C with a base of 16. So that's all, and thank you.
So I will be discussing the conversion of a number system to another. So for example, we have here 360 in decimal number system, so we use sub 10. So in the past reporter, the one who discussed it. So in rearranging this number, we arrange it from left to right, right to left. So 0, the arrangement of it is 0, then in 6 is 1, and in 3 is 2. So after that, we will multiply it to 10. So 3 times 10, then the arrangement of them, which is raised to 2, then plus 6 times 10, then arrangement is raised to 1, then 0 times 10 is equals to 0. So the sum of them is 300 plus 60 plus 0. Then the total of them, the total is 360. So it's just the same value, the given number. So in the octal, so this is decimal, octal. So in octal, we use as 8 subunit. So 8. Then arrange them 0, 1, and 2. Then multiply them by 8. 3 times 8. 3 times 8. Then arrangement of them 6 times 8. Then arrangement of them 0 times 8. Arrangement of them. Then sum them. Get the sum. 192 plus 48 plus 0. So the sum of this is 240 sub 10, because the decimal equivalent of this 316 to the octal number system is 240 sub 10. So let's move to hexadecimal. Hexadecimal. So in hexa, we need to use 16 subunits. 16. So multiply them to 16. Arrangement. 6 times 16. Arrangement. 0 times 16. Then and to sum this, the sum of this, when we compute this, so let's make it quick. So the answer is 364 sub 10, because of the decimal equivalent of this number into this number, hexadecimal number, the equivalent sum to decimal is 864 sub 10. So let's move to binary. So we have, in binary we have two digits only, so 1010. So rearrange them, arrange their value rather 3 2 1 0. Sorry, 3 2 1 0. So multiply them to sub 2, because in binary we has only 2. 1 times 2, then 3 plus 1 times 2, then 1 times my bad, 0 times 2, then 1 times 2, and 0 times 2, 0 raised to 0. So get the sum is equals to 10 sub 2. So that's it. That's how you convert a number system into another number system.